Today, we're going to introduce you to our Refinery Incident Prevention System. Our system is designed for implementation in a refinery environment where real-time monitoring is not just beneficial, it's crucial. We've developed a comprehensive solution that continuously monitors data from critical equipment and components throughout the refinery. At the heart of our system is a centralized main control room. This serves as the nerve center, overseeing the entire refinery operation. All data from across the facility is centralized here, allowing for comprehensive monitoring and rapid response to any emerging situations.
Our refinery control system is based on a layered modular architecture. At the top, the user interface allows operators to interact with the system utilizing .NET Windows Presentation Foundation (WPF) XAML for UI design. The security layer just below manages authentication and authorizations. The core of the system is the business logic layer, which processes data and executes control algorithms. We use two databases, SQLite Relational Database for local storage and MongoDB Atlas NoSQL Database for remote storage. Communication with physical equipment is managed by a dedicated layer using MQTT for real-time data exchange between the control room and refinery sensors actuators. In developing this system, we focused on two critical quality attributes: security and availability. Security is critical because any breach could lead to catastrophic consequences. Unauthorized access or modifications could mask dangerous conditions, trigger incidents, or compromise sensitive data. In a refinery environment, these risks could result in environmental disasters, significant economic losses, or even loss of life. Availability is equally crucial because our system must operate continuously to ensure safety. Any downtime could mean missing critical data, indicating an impending incident, preventing timely responses, or creating gaps in data that lead to flawed decision-making. In essence, if the system isn't available, it can't prevent incidents. Together, these attributes ensure our system is both trustworthy and reliable, capable of maintaining safe refinery operations 24/7. To ensure these attributes are maximized, we have used a variety of tactics. For security, we've employed several key tactics. First, we've implemented a robust authentication system with different ranks to different types of employees, giving each a predefined set of actions they can perform. If an employee attempts to access the control room dashboard without sufficient privileges, the access is refused and a superior-ranked employee is notified. If an employee or a malicious intruder enters incorrect credentials more than 3 times, that section of the system enters lock mode, preventing further access attempts to the dashboard and sending an alert to the superior. Our system implements a role-based authentication by defining 3 employee ranks with minimal access for each: operators, senior operators, and supervisors. Operators can monitor temperature and humidity sensors, as well as alerts and automatic procedures. They can also perform non-critical operations like sensor recalibration. Senior operators have access to all operator functionalities and can view logs of alerts and automatic procedures. They can also perform critical operations such as machine restarts and emergency shutdowns, but these require 2-factor authentication and superior authorization. Supervisors have access to all senior operator functionalities and can view logs of employee access, including login attempts and multiple wrong attempts. They can authorize critical operations initiated by senior operators, enable or disable sensors, and set sensor alert thresholds. If suspicious activity is detected while the employee is logged in, they are logged out and the system enters lock mode. To ensure high availability, we have implemented hardware redundancy, especially within our sensor network. Redundant sensors are in place for each critical parameter, guaranteeing continuous monitoring even if one sensor fails. We employ cross-validation to verify the accuracy and coherence of sensor data. Under normal conditions, we use data from the first and second sensors, comparing their values for consistency. If a failure or incoherent values are detected, the faulty sensor is identified and removed, and the third sensor, our second line of defense, is activated. In the event of a faulty sensor, an alert is always sent to a superior. Our system also includes automatic procedures that activate without employee intervention to prevent incidents. For example, if the temperature or humidity of a certain machine becomes too high, the cooling system is automatically activated. These automatic procedures ensure rapid response to potential issues, enhancing overall safety and reliability. The history of all the automatic procedures can be viewed by the supervisor rank in the dashboard. To facilitate future data analysis of sensor data, we log all incoming sensor data upon reception. These logs are transmitted to a remote server separate from the refinery's local server to safeguard against data loss during incidents. On the dashboard, these data are graphically represented to visualize the consistency of values over time. This visualization enables us to extract insights and identify patterns from sensor anomalies, aiding in proactive incident prevention and system optimization.
To further enhance availability, we have implemented automatic periodic backups of our local database to a remote server, ensuring that sensitive data is preserved in the event of an incident. Given our system's reliance on continuous sensor data monitoring and processing, we have mitigated the risk of a single point of failure by deploying multiple calculation units. These units collaborate on data calculation and validation tasks, ensuring uninterrupted operation. If one unit fails, another seamlessly takes over, maintaining system reliability and performance.